Hello everyone, my name is Abhinav Kochar and my topic for this presentation is Finite Automata with Outputs, which is Moore and Mealy machines. I'm from the batch 11 from Finite University and my roll number is E20CSE191. Going ahead, we will discuss about finite automata with outputs. We have recently previously discussed about finite automata without outputs and with outputs. So this is the classification of finite automata. And going ahead, there is a part of finite automata which is finite automata with outputs, which consists of DFA, NFA, and NFA with epsilon. DFA is called deterministic finite automata. NFA is called non-deterministic finite automata. NFA with epsilon is non-deterministic finite automata with epsilon transitions. So as we've discussed in the DFA and NFA, there are final states and there are initial states and there are transition states, and but there is no output. There is no output to these things. There is like infinitely recurring. They are just an expression of a language in terms of diagrammatically in automata. But going ahead in the finite automata with outputs, there are two types, specifically Moore machines and Mealy machines. Moore machines and Mealy machines are a representation of automata which describe finite automata with outputs. These machines, these examples give us the outputs required for a specific language or a specific output designed out of a specific language. So going ahead, we'll discuss what are Moore and Mealy machines. This is the topic for today anyway, and let's start with Moore machines first. So Moore machine is a finite state machine whose output values are determined solely by its current state, which means if in a Moore machine, the output values would be defined by the state of the transition, which means the outputs are defined by the states. In an automata, there are transitions, then there are states. And in a Moore machine, the outputs are defined by the states in a Moore machine. So going ahead with classifications of Moore machine and we'll go more descriptive in this, going ahead with this. So a Moore machine consists of more than states. Characteristics of Moore machine are ahead, by the way. So a Moore machine consists of more than states, more than the Mealy machine. Its output does not depend on the current input. It depends only on its current state. It places its output on the transition whenever a change occurs in the state. The output function's value becomes a function of its current state along with changes at the edges of the clock. The state and output both change synchronous to its clock edge in a Moore machine. One requires more logic for decoding and the output. As a result, it leads to more delays in the circuit. Generally, these react after one clock cycle, and one requires more hardware to design. A Moore machine the states for synthesis required for this machine are also more. It is very easy to design. You can refer to the counter as Moore machine. It can be defined as a six tuple where Q naught, epsilon, O, del, and lambda, where Q is the finite set of states, Q naught is the initial state, epsilon is the input alphabet, O is the output alphabet, del is the transition function which maps Q naught cross summation which gives Q, and lambda is the output function which maps Q which gives output O. So as we can see in the diagram of a Moore machine, there is an input state, and as you can see in every state there is an output. Like in the first state Q naught slash 0, it's written. So in the first state Q naught slash 0 0 is the output of the state, and then Q naught goes to Q1, and Q1 there is a transition 0, and as soon as it reaches Q1 there is an output 0. So the transition defines the output. As Q1 goes to Q3, it gives an output 1. Again, from Q0, if it goes to Q2, it gives an output 0. And in a Moore machine, there's a very specific definition. The output is initially defined first, which means every output of this Moore machine will be starting with 0. Which means if say I put in the transition of Q0, Q1, Q3, and Q4, the output would be 0, 0, 1, and 1. which means like if I put in an input of 0 1 0, which it will give an output of 0 0 1 1, as the output is defined by the transition. And going ahead, we'll study about the Mealy machine. Mealy machine is a finite state machine whose output values are determined by both its current state and current inputs, which means its outputs are defined by both its current state and current inputs. We'll study about this in the for the slide. It can be defined as q naught epsilon o del and lambda, where q is finite set of states, o naught is the initial state, sigma is the input alphabet, o is the output alphabet, del is the transition function which maps q cross lambda, which gives q, and lambda is the output function which maps q cross lambda, which gives q. So as you can see in the diagram, there is an initial state and this does not have an output. In Mealy machine, the states do not have an output, but the transition has an output. As you can see, there is as q naught goes to q1, there is a transition of it's given 0 and the output is 0. And also, if it's given 1, the output is also 0. So anything from this q naught going out will give an output 0. And then there are transitions from q1 to q2 and q2 to q1, which give respective outputs like 0 and 1 to the respective inputs. And to the theoretical definition of characteristics of Mealy machine, a Mealy machine has fewer states as compared to a Moore machine based on its present state. And the current input, the Mealy machine alters its input, it places its output on the transition. Every Mealy machine reacts to inputs comparatively faster. The reaction occurs in a very same clock cycle when the input logic is done in the present state. The value of the output function becomes a function of transitions and changes. A Mealy machine generally requires only a very few states for the process of this synthesis. The asynchronous generation of output through its state alters to synchronous on the present clock. It requires very less hardware for designing a Mealy machine. The designing process does not need to be very easy. You cannot refer to the counter as a Mealy machine. So till now we've learned about Moore machines and Mealy machines individually, and what these things do and what are the functions of these things. Going ahead, we will study about the comparison between these two. But first, I would prefer to define a little bit more on Moore and Mealy machines. So as I've understood that in a Mealy machine, there is every output is described on a, what do you call it, on a transition. But in a Moore machine, every output is described on the state, which means these are two different things. And the transition from Moore to Mealy is quite complicated. We'll study going ahead in the PPT. So, what are Moore and Mealy machine? So, Moore machine versus Mealy machine. Moore machine, the output depends only upon the present state, whereas in the Mealy machine, output depends only upon the present state as well as the present input. In a Moore machine, if input changes, output does not change. But in a Mealy machine, if input changes, output also changes. As you can see, in a Mealy machine, it's based on the transition. So if the input changes, the output will change. And in a Moore machine, there is less hardware requirement for circuit implementation. But in a Mealy machine, there is more hardware requirement for circuit implementation because there are more. The output is based on transitions, and the hardware requirement is more due to that. And in Moore machine, they require react faster to inputs because as the outputs are based on the states, not the transitions, and they are react faster to outputs. But in a Mealy machine, they react slower to inputs once clock cycle later, which means one clock cycle later. In a Moore machine, output is placed on states, whereas in a Moore machine, there is asynchronous output generation, and output is placed on transitions, which we've thought about. And in a Moore machine, there is synchronous output and state generation, obviously. And Moore machines are generally very easy to design, and Mealy machines are pretty difficult to design in an automata. So this was the difference between Moore and Mealy machine. I hope it's pretty accurate and clear to everyone hearing this. So going ahead, we will talk about the transition of a Moore machine to Mealy machine. So we can draw a Mealy machine table. So to transform a Moore machine to Mealy machine, first we need to make the transition table of these machines. So first we make the Mealy machine table and make the transition states and write the symbols and everything, and then copy the present state and the next state column of this state into the table. We copy it to the table, and for output column, the next state, we check the present state and its output generated to the Moore machine table. For example, if output is generated by state qy is m, copy this output to the output column of Mealy machine table, where table whatever qy is present in the next state. So there would be two columns. One is a Moore machine column and one is Mealy machine column. From Moore we have to convert to Mealy. So we have the transition table of a Moore machine. We have to create a new table for a Mealy machine, for a Moore machine, uh, for a Mealy machine from Moore to Mealy, and then we go ahead with transitioning. We go ahead with putting in the inputs to respective columns and spaces, and then going ahead we get a transition table of a Mealy machine which we can draw out in Automata. So this is how a conversion of a Moore machine to Mealy machine works. Going ahead, we will study about the Mealy conversion of a Mealy machine to a Moore machine. So in the conversion of a Mealy machine to a Moore machine, we find out different output generated with Qi in the next state column of Mealy machine. Then split two into different states depending upon output generated with it. For example, if output generated by Qi is 1 in the first state column and 0 in the next state column, then split Q1 into 2, Q1 naught and Q1 1. Follow the above steps for all states. Now copy the present state and next state in Moore machine format and output. The next state are common. So basically, again, what we do in the transition of a Mealy machine to a Moore machine, we derive the Mealy machine transition table, and then we make a Moore machine table, and then we put in the respective output generated within Qi to the Moore machine table. And if the output generated by Qi is 1, and there are two outputs getting out of it, we split it into two parts, q1 and q0, and this would be repeated for every state, every transition, so that the Moore machine automata is perfect. It is defined. Uh, it is a DFA. So it is not a DFA. It has perfect outputs. So going ahead, this is the transition of Moore machine to Mealy machine. We will revise everything from start to now for a bit, and then we will end the PPT. So since the starting, we've learned about finite automata with outputs, which is Moore and Mealy machines. Now we've studied about Moore and Mealy machines and how the outputs are derived and everything with the outputs, and we already know what without output automata is, which is DFA, NFA, and epsilon NFA. Going ahead with the Moore machine, we've read the definition and what a Moore machine is theoretically. Then we have described the tuples and how a Moore machine function, what are the characteristics of a Moore machine, and how everything in a Moore machine functions. Then going ahead, we talked about Mealy machine and its definition theoretically, and then we described about the tuples of a Mealy machine and also its characteristics and how it functions and how it presents outputs. Then after that, in this summary, we are going to talk about Moore machine versus Mealy machine, which we discussed in the video previously. And then after that, there was a talk about Moore Mealy conversion. So there were in Moore Mealy conversions, we taught transition tables. We describe the outputs and the elements, and then we recreate the automata according to that. And the same repeats itself in the Mealy machine transition table. So this has been my presentation again, and I thank you for your time, and I respect the time you've given to this presentation. And this has been a great time teaching finite automata with outputs. Myself, Abhinav Kochar. I am from batch 11, and Bennett, a student of Bennett University. Roll number is E20CSE191. Thank you. I thank Simranjeet sir for his guidance in helping me with this presentation, and So it was his knowledge, his wisdom, his tutorials, and his teachings in the classes which helped me through this presentation. And by his grace, I was able to finish this project of mine. And I respect and thank Simranjeet Singh sir for helping me throughout the presentation and this semester for automata theory of computation. Thank you.